And another person I'm excited to have, not quite here, but not too far away, Fei Fang. So unfortunately, Fei had to head back before her talk could take place, but she's very, very kindly agrees to spend her Sunday, part of her Sunday, zooming in from, I assume, CMU in Pittsburgh rather, but to talk to us about game theory and machine learning for addressing societal challenges from theory to real-world impact. So just give a little, by way of brief introduction, Fei is a Leonardo Assistant Professor at the Institute for Software Research in the School of Computer Science at Carnegie Mellon University. And before joining CMU, she was a Postdoctoral Fellow at the Center for Research on Computation and Society at Harvard, hosted by David Parks and Barbara Grosz. She received her Ph.D. from the Department of Computer Science at the University of Southern California, advised by Milind Tambe, who's also now at Harvard. You'll notice a theme here. And her research lies in the field of AI and multi-agent systems, focusing on integrating machine learning with game theory. Her work has been motivated by and applied to security, sustainability, and mobility domains, contributing to the theme of the AI for social good. She's a recipient of the IEEE 21 Computers and Thought Award, and she was named to IEEE Intelligent Systems AI's 10 to Watch list for 2020. She received an NSF CAREER Award in 2021. So quite a long list, quite a ridiculous trajectory so far. It's a really great pleasure to be able to introduce Fei. Fantastic way to round off the summer school. So Fei, when you're ready, over to you. Thank you.
Yeah, thank you so much for the introduction. Thank you all for coming to the talk. Yeah, it's my great honor and pleasure to give the talk here. I was there with you guys at Santa Cruz, but I had to head back. So I have to give the talk remotely. And thank you for the accommodation. So I'm very interested in this societal challenges, and I know that in this real world we see many challenges that we're facing, and many of them actually involve multiple decision makers whose interests are not perfectly aligned with each other, and ranging from security to environmental sustainability to transportation to many other problems. And what I've been working on is to develop AI methods to help address these challenges, and that's going to be the first part of my talk as well. And also, from my experience working with different problems in the real world, I'm also discovering new fundamental challenges that is still under-addressed by the AI community and try to bring more solutions to those. And that will be the second part of my talk. And then after that, if we still have time, I would love to talk more about our very recent work and what's next. So when people talk about game theory and machine learning, the first thing that people come to mind is probably all these AI agents for games, for Go, for StarCraft, for Poker, and many other games that, some of them, of these are maybe your favorite board game or video games. And they use game theory, they use multi-agent reinforcement learning to try to address these games, and then trying to build AIs that can outperform humans. And I myself also contributed to some of these kind of works for play card games or board games. And if we get time at the end of the talk, we may get to the werewolf one. That's a recent work that we had. But what I want to first and foremost to emphasize on is, with all these advances in AI for playing these games, how about the real world applications? Can we leverage these techniques or build new techniques that can be useful for the real world? The reason why I'm interested in the real world is, in the very first project in my PhD, I had been introduced to this real problem of protecting ferries from attacks. And there, we formulated this problem as a game between the US Coast Guard and the attacker. And then we formulate this as a stackable game so that the US Coast Guard is the leader or the defender, and the attacker is a follower, as the attacker would first conduct surveillance of the defender's strategy and then decide which target, which ferry to attack and when to attack. So here we can write down the game matrix with the rows indicating the possible patrol routes that can be taken by the Coast Guard patrol boats, and the columns indicating the target and time for the attacker to attack. And we assume this to be a zero-sum game, and we're looking for the strong stackable equilibrium, meaning we want to find a probability distribution over these patrol routes so that we can minimize the attacker's maximum expected utility. We solved this game with linear programming, where here the variables are the probabilities of taking each of the possible routes, And then this constraint is to say that the attacker would choose the target at time, target I and time t, that is leading to the highest expected utility for the attacker. And this work has fortunately been deployed by the US Coast Guard, and I myself also went to the Staten Island Ferry to see how the patrol boat are moving according to my algorithm. That gives me a lot of sense of achievement, and also it motivates me to do more work on the real world. And later on, like following this work, we have more and more work that is kind of using game theory for real world problems. And one of these recent ones is on peer review. I'm not sure if any of you submitting any papers to any of these conferences in computer science. And every year there are anecdotes or rumors saying that, there are some people who are colluding with their friends and then trying to get their paper in. Or there are some cases where there's some authority in some area, they just don't like certain type of paper, so they reject the paper as long as it hits some words that they don't like, right? And of course, this kind of things are not what the program chair wanted. So now we can actually similarly formulate this as a stackable game, with the leader being the program chairs and the follower being the malicious reviewer who wants to get assigned a specific paper that they're targeting to just make the paper accepted or rejected. And then following the same idea as what we had before, what we want to do is that we want to increase randomness in the reviewer assignment procedure, so that even if some reviewer wants to target a specific paper, it is hard for this reviewer to get that paper for sure by, say, bidding a very high willingness to own that paper, or even submit some papers that are like relevant to the target paper and nothing else to the TPMS system, where people are using the text similarity for measuring the matchness between the paper and reviewer. So there are people doing that, but what we want to do is that we kind of want to have the randomness in place such that even if they did all they can, they still cannot be guaranteed to get the paper that they want. And what does that mean? That means we're going to have this probability of a specific reviewer assigned to a specific paper. And in the past, this probability is either 0 or 1 when before we kind of consider introducing randomness to the process. And now we want to make this a number between 0 and 1, and we probably want to restrict this number to be not too high if we want to really minimize the malicious reviewer's probability of getting their target paper. But here we actually need to deal with multiple objectives. As we said, we want to minimize the maximum probability for some malicious reviewer to get their target paper. Since we don't know who is a malicious reviewer, what is their target paper, so what we can do is to consider this zero-sum case where we consider the worst case performance and then minimize that, minimize the probability that any reviewer can get assigned to any paper. But if you don't only do it this way, then you just have a uniform random allocation of papers, and then all the authors would complain, and reviewers would also complain that, the papers assigned to me are irrelevant to me. Right? So the other objective that the program chair cares about is to maximize the total matching score between the paper and the reviewer. So here, this SRP is basically the matchness between the reviewer R and the paper P. So we need to consider both objectives, and then the solution that we propose is just to treat one of them as a constraint and the other as objective. And this idea and this work has already been used in paper assignment in multiple conferences, including IEEE 2022, 2023, and GameSack 2022 and KDD 2023. So here, overall, in the end, what we get is such a linear program where we maximize the total similarity score subject to the constraint that the assignment probability should be no higher than some threshold Q RP. So this Q is something that can be chosen by the program chair. And then also we need to satisfy that each paper needs to get at least L reviewers, and each reviewer can review at most K papers. So this is what we had. And we were for the first time, we kind of introduced the randomness to the entire peer review procedure. And then last year, we kind of reflected on what we had before from the deployment. And we noticed that, in fact, there's still a lot of room for improvement in terms of the randomness. So think about a very special case. It's a simple, small conference with only 2 papers and 2 reviewers. And they have equal matchness score per se. And now we try to solve the linear program that we just mentioned, but with the threshold, like the maximum probability that can be allowed to be 0.8. Then, since this is a linear program, so we would typically get a vertex solutions through simplex or other algorithms, and we will get this assignment of like 2 edges will be assigned with probability to 0.8 and the remaining to be 0.2. But in fact, we know that in this particular case, since everything is symmetric or just the same, the ideal case is just uniform random. But we cannot get that solution because the linear program itself does not incentivize that truly random, like more random solution. So we propose to address this issue by perturbing the objective function a little bit. So here, instead, we want to make the objective function as the score, the similarity score, SRP, times a function f of the assignment probability, XRP. And then this f is a function that is not decreasing and concave, so that if you increase the probability, the XRP, you gain something in SRP, but you get lower gain as your x is higher. The marginal gain is getting lower and lower. And by doing so, we can incentivize it to have more randomness whenever possible. For example, if there's a tie, just as we see in this case, it should just distribute the probability uniformly randomly. And this, by doing this, we can also show theoretically that this can strictly improve randomness when the similarity matrix is satisfying some properties like blockwise dominant or discrete at random, where the formula, the blockwise dominant, is basically saying that, oh, your conference has several subject areas, and then the reviewers in the same subject area as a paper would have a higher matchness score or similarity score, and then if the reviewer is going to review a paper outside of its own subject area, then they have a lower similarity score. And the discrete at random means that your similarity values, the score values that you get, is only going to be from a finite set. So this, because of this improvement on the randomness, NeurIPS 2024 this year adopted our algorithm to do their paper assignment. So now we've seen 2 cases of like defender and potential attacker type of thing, and let's consider a third one. And this one is initially probably not so obvious, but it's actually very similar. So we want to protect the wildlife from poaching. And we can formulate this problem as a stackable game, or just a stackable game between the rangers and the poachers. So the rangers are the ones who are designing the patrol routes every day, and the poachers are the ones who are going to observe the patrol strategy by the rangers and decide where to place the poaching tools, like what you see in these images. And the new challenge here in this problem is that the poachers are not perfectly rational. Comparing to the previous 2 cases that we've seen, where we consider a zero-sum game and maximize the minimum case or minimize the maximum case, here, the poachers don't work that way. Like, they don't have enough time and effort in their planning of their actions, and they're actually much less planned when they're taking their actions. But does that mean that we cannot do anything for it? Well, no, of course not. Instead, we can actually try to leverage historical data to try to learn the poacher's behavior. And then with the learned behavior, now we can use the game theoretic formulation to try to plan the patrols for the rangers. So we leverage the data from previous patrols and satellite imagery, and also additional domain knowledge from the rangers, and we developed a series of machine learning methods to try to predict the poaching threats. We are not going to go into the details of all of these. In the end, typically we use an ensemble of different machine learning methods to do the predictions and then do the planning of the patrol routes. And with our machine learning powered prediction and the game theoretic planning, we were able to work with WCS and Panthera and WWF and Uganda Wildlife Authority and RIMBA, several wildlife conservation agencies, to deploy these ranger patrols in the field. and in Uganda, in China, in Malaysia, and in several other areas. And the picture in the right is actually me walking on the patrol together with my collaborators in northeastern China, a protected area for tigers. So we've seen that through this field test, these AI/ML powered AI/ML and game theory powered patrols leads to much more findings upstairs, and also sometimes they also saw poached elephants. That's sad. But on the other hand, it means that if they could follow our suggested patrol earlier, then they could potentially have saved the elephant. So by now you've seen probably enough of these leader, follower, defender, attacker like games. So let's change to something that is a little bit less competitive. And we consider there are problems in the world that are still multi-agent, still not fully cooperative, but they are not as adversarial as what we just introduced. For example, the food rescue situation. So we know that food waste and food insecurity are big problems, and we want to rescue good food. And luckily, there are already some nonprofit organizations doing this. For example, Fall into Food Rescue. So what they do is that they have been in touch with grocery stores, cafes, restaurants. So if these places have not sellable but still eatable food, then they would contact the platform saying that we want to donate this food, but this food needs to be consumed very soon. And so the platform would then immediately post a request on their smartphone app saying that we're looking for volunteers to help us pick up the food from the donor and then drop off the food to the recipient. So the platform would choose a recipient for each of the donated food, and the volunteers like me would go and pick up the food and then send it out to the recipient and get a food rescue hero badge. So in this problem, if you think about it, there are many, many decision makers. There are the platform, there are donors, recipients, and the volunteers. Each individual volunteer is an individual decision maker. And now the problem that are faced by the platform is how can they improve the operational efficiency? Because one pain point they have is that they are always uncertain about whether rescue will be claimed by the volunteers. Because keep in mind that those volunteers are individual decision makers. They are not just following the orders of the platform, right? So what can the platform do? The only thing they can do is to communicate and coordinate with the volunteers so that they can get more of those donated food completed, the rescue request completed on time. So what they do currently, previously, is that once the rescue is published, they will send out the first wave notification to all volunteers within 5 miles of the pickup location. And they will wait for 15 minutes. If no one picks up during this time, they will notify all the volunteers on the platform. And if it is already very close to the pickup deadline of the food, then a human dispatcher would jump in and try to contact individual volunteers by texting or phone calls. But of course, they don't have enough human dispatchers who can always do this texting and phone calls every time. And also, they don't want to send out too many notifications to the volunteers because volunteers would get fatigued and they would just drop the platform. And what we have doing is trying to help them improve this communication mechanism. At the very beginning, we were like, okay, let's just stick to what they have and only change the numbers of 15 minutes, 5 miles, and 60 minutes to something different number, and then to see whether that can improve it. And we do have a mathematical formulation, and they deployed it and also see the improvement. At that point, they were like, oh, your mathematical backed stuff is somewhat working. So now they have trusted in us. And then at that point, we were like, okay, can we try something that is even better than what we had did before? That is machine learning based notification. So we built this machine learning model that can predict the probability that a particular volunteer may be interested in claiming a particular rescue. And using historical data, we're able to train the model. And with this, the easiest option that we can think of is definitely like make the prediction whenever a new rescue comes in, and then send push notifications to the top K volunteers. And we checked on the historical data, if we did it this way, can we get any improvements? And indeed, what we found is that the hit ratio at top K, meaning the percentage of rescues that can be claimed by volunteers in the first batch of notification, can increase from 0.44 to 0.73. So that's a huge improvement. And the Food Rescue folks are also impressed by this. So we decided to run out to do a field test. So we did the first randomized control trial in this food rescue domain, and we tested 3 conditions. The control condition is basically the default distance-based notification scheme. And the second one is our machine learning-based notification scheme. And the last one is to have 80% of the time using the machine learning one and 20% of the time just notify volunteers purely randomly. And what we had from the field test is that indeed the machine learning-based one can significantly improve the hit ratio, and also it can significantly improve the claim ratio, meaning the percentage of rescues that will be claimed by volunteers overall. So this is great. And for the machine learning plus random one, you may notice that this is not too different from the control. That's because like the machine learning part is indeed improving, but the random part, if you just randomly selected volunteers to notify, it's even worse than the distance-based one, the default mechanism. So that's like what we see from the results. And also we noticed that especially for the areas where the donated food is hard to find volunteers, by doing the machine learning-based approach can significantly improve the claim rate and hit rate. So hopefully by now, I've convinced you that by combining game-theoretic thinking and multi-agent learning or machine learning in general, we can develop AI tools, AI agents that can be useful for real-world problems. And all these things that we've discussed today have already led to actual deployments in the field. And then in the part 2 of my talk, I'm going to talk about what are the things that we notice as like the more fundamental challenges as we work on these different problems and how we develop methods to address those. So the first challenge we see is that sometimes there are these undeniable collisions, secret collisions among agents. Like in peer review, you have the reviewers colluding with some authors. And then in ride sharing, there are like drivers colluding with each other to turn off their apps simultaneously, and then try to trigger some like price increase, and then they turn back on their app, and then they can earn more money. And in auctions, sometimes there are also like collusions to some extent. And now, as we witnessed all these existence of secret collisions, the natural question to ask is, how can we figure out the collision among agents? And this is also very important for regulatory purposes or for constructing better mechanisms. And now the problem that we want to study is that you have a bunch of agents, and then some of them are colluding with each other, and we don't know who are colluding. So what we want to do is we want to recover the unknown collision structure by observing the interactions of these agents in some games designed by us. So we want to design the game, and then we want to observe their action or behavior, and then we want to recover the collision. And to start with, we use the simplest assumption, assuming that every time we design a game and we provide a default strategy profile, and we want to observe if this default strategy profile is a Nash equilibrium. And think of the simplest case where you have 2 players and then you ask them to play Prisoner's Dilemma. If they play corporate, then you know that they are in a collision. And of course, here we're assuming that they're all rational players, and they kind of, if they're not colluding, they should play Nash equilibrium. So if you give them a defect, and if they deviate from that and decide to collaborate, then this is not. Then you know that these 2 players are colluding. Otherwise, they're not colluding. Now, since you have many players, what you can do is that you just every time pick only 2 agents and let these 2 agents to play Prisoner's Dilemma, and let the other agents to do nothing. And then by doing so, every time at least you recover a pair, the relationship between a pair of agents. But this is not super efficient because you will need and choose 2 games in total to figure out the entire collision structure. So what we do is that we propose this iterative grouping algorithm for learning the collision structure. What do we do? Well, we're going to determine the agent collision one by one. So let's say we're currently looking at agent I. Then we're going to let every other player to play this prisoner's dilemma. We call it the normal form gadgets with player I. So it's like I is playing with agent 1, agent 2, agent 3, each with the prisoner's dilemma all together. It's like in one game, we kind of there are multiple prisoner's dilemma ongoing, and then we ask them if defect. Always defect is the Nash equilibrium, is the one that they are willing to follow. And if it is indeed a Nash equilibrium, then that means agent I is not colluding with any other agent. And if it is deviating, if they say that the always defect is not a Nash equilibrium, then at least we know that agent I has a teammate. So then the easiest thing we can do is to just divide all the other agents in half. And then just to do this again separately for each of the halves, and then figure out where is the teammate. And continue doing the binary search, we can at least identify one teammate of agent I. And once we find out a teammate of agent I, we can just merge that player player J with a player I into a single player, and then we can continue the process. And by doing so, we can recover the collision structure with O and log n games. N is the number of players in the, that we are trying to recover the collision. And this is a very kind of simplistic scenario where you assume that you can just design any game you want, like Prisoner's Dilemma, and let people come to play your game. And however, in practice, this is probably very hard to achieve. So we also studied other more restricted classes problems where, let's say, the I, as a learner, cannot design any game. Instead, I can only, say, design an auction with the personalized reserve price. It's like I cannot control the item being auctioned. I cannot control the valuation of the item to individual bidder, but I can control the personalized reserve price in the auction, so that if someone bid a value that is lower than the personalized reserve price, they cannot get the item anyway. And we show that even with this kind of restricted classes or any other several other special classes, we are still able to learn the collision structure with O and log n games by just extending, well, not trivially extending the iterative grouping idea that we had before. So now that's the first challenge, that fundamental challenge that we see and derive from the real challenges. And second one is that we do notice that many real problems are not zero-sum. Like we do use zero-sum a lot in our actual solutions for the real-world deployment because they're simple. But it doesn't mean that they are actually zero-sum. Right? It's like most of the cases, the agents are not fully cognitive, they're not fully competitive. Even in the security game case, where you have the defender and attacker, the attacker may value targets differently from the defenders. And so in this case, what we need to do is that we need to compute the equivalent solution for such games. The general sum games are much harder to solve than zero sum games. And now the fundamental question for us is that can we design better algorithms to solve the general sum games more efficiently? And we leverage the idea from solving zero-sum games. We know that for solving large zero-sum games like Go, people have used the idea of functional approximation. Like, for example, they use a value function to approximate how good or bad each state is, so that they don't, like, on the right, we have the game tree. With the value function, instead of representing the entire game tree, they can kind of abstract out a big portion of the sub-game tree with this single value of v, right? To say that, oh, if you get to this, then the rest of it, you're going to get this much as payoff. So by doing so, that can make the game much, much smaller, and then it becomes much easier to solve the smaller game. And now the remaining question is to learn the v's, the value function of the states, and typically people use a neural network and then try to approximate the values. By doing so, they can solve the zero-sum games more efficiently than before. Now, what we want to think about is how can we apply this idea of using functional approximators to general sum games and in a principled manner. And here we started with the stackable games because we're mostly familiar with the stackable games. And here, what we noticed is that we cannot use a single value to represent the game because of the fact that this is a general sum game and it's a stackable game that we're considering. So instead, we turn to the concept of enforceable payoff frontiers, where we want to say that we kind of want to have a range of payoff pairs that can be achieved by the players in the subgame. So we kind of want to use this enforceable payoff frontier to summarize a subgame. Now consider the example game that we show on the left, where we have only just 2 layers of the game, where first we need the player A moves and then the player C moves. And then at the A node, if the player can go left to go to the node C, the player can also go right to go to a state, an at-leaf node where player 1 is going to get the utility payoff of K1 and player 2 is going to get a payoff of K2. Now, if we want to summarize the subtree shaded in green, what should we do? We cannot use a single number here because like the value of K1, K2 matters a lot to the how we should summarize the range of C. So what do we do here? Instead, we are going to put the follower utility on the x-axis and the leader utility on the y-axis. And what we want to see, what is the kind of the pairs of utilities that can be achieved here. And we notice that, if we get to this leaf node, we'll get 1 and 100. And if we get to this leaf node, we get 50 and 3. And then the entire line here is achievable. And then with the entire line, it just captures the right trade-off between the 2 players. And of course, here is linear in this subgame, but in general, it is not necessarily linear, but it can be shown that it's piecewise linear. So essentially, we can use a piecewise linear function in this leader-follower utility space to represent a subgame. Now, the problem is relatively clear that we want to kind of learn this enforceable payoff frontier instead of learning a single value for each subgame. So we use speed and value iteration to learn these EPFs, and we use a neural network to represent such a piecewise linear function. And then we train the neural network through minimizing the Bellman loss, try to have these EPFs learned to represent, have these neural networks to learn to represent the EPFs. So we see that with this, we are able to actually do a reasonably good job. Here, we're kind of minimizing basically the similarity, maximizing the similarity between the predicted EPF and the true EPF. And in the experiment, we show that we are able to learn the EPF really reasonably well. And one more thing to notice here is that we actually care a lot more, mostly, we actually only cares about the part that is going this way, like the Pareto frontiers per se, on the downward side. And because that's what is going to matter when we propagate it back to the root of the game and to solve it. So think of the case that now we're using a piecewise linear function to represent a subgame. So what we want to do in the end is that we are able to kind of represent many of these subgames, and then we solve the entire game with those subgames replaced by these EPFs. And if we made any errors in this part, in the part that is non-decreasing, then it doesn't matter much to the actual solution. It is the decreasing part that matters to the final solution. And from this experiment, we showed that we are actually approximating that part really, really well. And using this approach, we can mostly outperform the subgame perfect equilibrium that can be found. So now we also tested on much, much larger games where it is very, very hard to solve using the existing approaches, and using our approach, we're able to find optimal strategy in almost all cases. Okay, so the last challenge that I want to mention is to get interpretable strategies for real problems. Because if you want to deploy some AI-based agent for these societal challenges or other real-world problems, we need the stakeholders' approval. But stakeholders, many of these humans, would like to understand what the agent is doing and why it does so that they're willing to rely on the agent to make some decisions, or they want to collaborate with such an agent where they can know what they're doing, or they can even learn from the agent to help them to do better decision making in the future. And so, inspired by this, we decided to work more on this interpretable policies for sequential decision making in multi-agent scenarios. And we've specifically focusing on getting decision tree policies because this is the simplest interpretable form of policies. And here, essentially, we know that most of the existing multi-agent learning-based approach to solve those complex sequential decision-making problem in multi-agent setting would end up getting a new complex neural network-based policy. But we wanted to get this decision tree policy. So how can we do it? Well, the simplest thing is to ignore the multi-agent perspective, just treat this as a single agent problem. So initially, we use the standard multi-agent reinforcement learning technique to get to the neural network policies for each agent. And then for each individual agent, we just treat all other agents as part of the environment and say that, oh, can I just approximate this agent's behavior with a decision tree? Then, of course, you can do imitation learning, or you can do what we the Viper algorithm. This is a paper that has been proposed several years ago, where you do the imitation learning iteratively so that you can get the decision tree policy match better of the agent policy, the neural network policy. You can do it this way, but notice that this is a multi-agent scenario. Actually, there are a lot of coordination between the agents. If you just treat the other agents as environment and then do your extraction of decision tree, then it could happen that agent one has a bunch of cases where it's kind of the decision tree predicted action is different from the neural network predicted action. And then this happens also for the other agents. And these mistakes are not well aligned such that they are miscoordinating a lot. So we want to address this hugely miscoordination issue that is exacerbated because of this extraction of decision tree policies. So we propose to use this to do this multi-agent Viper, which is try to train each individual agent's policy in a joint fashion so that you can expect what the other player would do as they are going to train a decision tree policy instead of their original neural network-based policy. And now we tested our algorithm in the scenario where we have 2 defenders and 1 adversary. And then we replaced both defenders with this decision tree policies. And we noticed that with this our algorithm, MA Viper, we can achieve much better coordination between the defenders so that the joint performance of the defender is way better than the other methods. Okay, so now we've already went through most of these challenges, and now what's next? But we don't have enough time. We're not going to go into the details. I just want to briefly mention what I see as something that I want to continue working on. One is large language models for societal challenges. We've seen all these different challenges there, and we've also seen the capabilities of these large language models. How can we leverage them to build better solutions, AI-based solutions for these societal challenges? We've already had some attempts. For example, we tried to build this media monitoring tool for helping the conservation agencies to take timely actions. And this work has already been deployed by WWF in multiple places like India, Nepal, and Colombia. And we've also received a lot of positive feedback from them after the deployment. And in addition to this, very recently, we also tried to build the simulated patients for training mental health professionals. And in this work, we're using the language model as a simulated patient, and we also did consult with psychiatrists and cognitive behavioral therapists to try to build the simulated patient in a way that is closer to the actual patient that they may face in their real life. And we have the trainees who can come and interact with the patient and trying to recover the cognitive model of the patient as a way to training them. So, and then we can also provide them feedbacks, the trainees feedbacks, to help them get better in their skills. And now, in addition to this leveraging large language models for societal challenges, I'm also very interested in this combining large language models with multi-agent systems, because that is the future. We've already seen that is the future. As I mentioned at the beginning, we do have some initial attempts on building strategic language agents, where we want to empower large language models with the capability of strategic thinking. And also, we use reinforcement learning to strengthen the decision-making capabilities of the players. And we focus on the werewolf game, a social deduction game, and we want to design the agent who can strategically discuss with other player and then win the game. So, in a nutshell, what we do is that we have several modules. We have the first module, the deductive reasoning module, to help the agent to reason about the current situation. And then the second module is to generate possible actions for one player, the player who's going to act right now. And the third one is to select from these possible actions using a reinforcement learning-based training. So that's kind of the initial attempt, and we also have several ongoing work along this line, and happy to talk more offline on that. And with that, I'm happy to take questions.
Hey, thanks very much, Fei. Hopefully you can hear me all right. Unfortunately, I didn't unmute the microphone in time for you to be able to hear the applause. And we don't have the webcam here today pointing in the opposite direction. So you'll just have to take my word that there's a big crowd of people out there who just applauded for you.
Thank you.
So I'll remind everyone that if you want to submit questions to Fei, then you can do so via the Slido app that you should have in front of you. And I think I will ask the first one, which is on the top of the list, as soon as my thing loads, which is, for some reason, it's failing to do so. Let me just check. Okay. So, first question is as follows. What are some of the limitations of the ML and game theory framework in deployment, and how susceptible are these systems to being gamed by bad actors?
Yeah, that's a very good question. So the first, what is the main limitations? Like one big limitation I witnessed is that in many problems, they don't need game theory. Like we have some like large language model for societal challenge kind of work. And we notice that for many of those scenarios, game theory is not so necessary. Game theory is needed when there are this kind of strategic thinking needed, right? And then if we do have that there, then the next challenge is how to really specify the input needed for the game theoretic model. For example, in the security game setting, we need to figure out, oh, if the attacker does this, defender does this, what is the payoff for the defender and the attacker? And there's no like machine learning like way to do it. It's mostly dependent on the stakeholders' input. For example, in the ferry case, we learned from the stakeholders that it's like when the ferry is getting closer to the terminal, it is more important because the people who are waiting at the terminal may also be impacted if there is an attack. So essentially, it's like the stakeholders who are going to provide those input. And how accurate is their input? That's definitely a challenge. And sometimes we need to have multiple meetings with the stakeholders to figure out what is the best way to model the payoffs. Yeah, and the second part of the question, can you repeat it again, the second part of the question?
Sure. The second part of the question was, how susceptible are these systems to being gamed by bad actors?
Yeah. Yes. So that's a very good question too. So we, in our first and second example that we show, where we use the stackable game model for the defender-attacker like thing, we always assume that the attackers are perfectly rational, and which is somewhat reasonable in these domains because we don't, first of all, we don't have much data, and the best we can do is to assume that they are perfectly rational. And the second thing is that it's kind of the worst case scenario. So if we are protecting against the worst case and they didn't do that bad, then it's kind of good for the defender. So it's like, I don't even worry too much about the attackers reading my paper and then deciding that, oh, they want to game the system accordingly, because what we are assuming is already the worst case. If they don't work perfectly rationally, then it's a game for the defender. But for the anti-poaching case, right, we kind of now rely on the historical data and try to assume that the attackers, the poachers, are not perfectly rational, and we're designing the patrols against such unboundedly rational poachers. But what if the poachers are actually smarter than what we thought? That's indeed a limitation, and we've also run various kind of sensitivity analysis in different models. In general, what we notice is that if the defender assumes the attacker to be very capable and the attackers are not as capable, then sometimes the defender loses a bit, for sure. But if the defender assumes that attackers are not capable, but the attackers are actually very, very capable, then the defender has the risk of losing a lot. So it's like, depending on the scenario, one might need to gauge how much rationality or how much capabilities you want to assume about the attackers. You don't want to overestimate too much, but you don't want to underestimate.
Nice, that makes sense. Thanks. The next question is a great one, I think. How do you identify and connect with organizations that would benefit from game theoretic and ML approaches to their problems?
Yeah, that's actually a very good question. So we started with the fairy protection one, and that one is because there has already been some successful applications of game theory for security prior to my PhD. And then after that, we started to talk to people about this like randomized patrol and how to improve patrol and such. And then we got connected with people at World Bank, at conferences or venues or symposiums or other like venues. And then they mentioned to us that there's the Tiger Initiative where they do this like patrols to save tigers. And then we learned more by talking to people who are doing this field and realized that indeed there's a lot of similarity. And in the initial thought is, oh, let's just apply the fairy protection idea to the web conservation. And then slowly we realized that it doesn't work, that there's a lot more research challenges to be addressed. So that's kind of how some of these connections get started. And then for the peer review setting, it's also like we've heard about this like gaming for a long time. And then finally, at some point, we were like, we have worked on this thing for a lot. Can we do something for addressing this issue? And this is more like based on our own experience of people gaming the system. And then we started to try to come up with solutions. And when we were working on this problem, the peer review one, initially we're not connected with any conference program committee or anything like that. But many of the authors, like including myself, Vince Conizer and Nihar Shah, we all had some experience participating in the conference organization, so we kind of know what's going on. So we ourselves are somewhat domain experts already, so we are able to do it from that perspective. And moving forward, I do see that if we see some gaming behavior there, then there's a potential interest of people who are managing the system to talk to us researchers who are doing game theory for real world problems and to see if there's a common interest. But I have to say that I would suggest not to bring the hammer and try to find the nail, because it's kind of hard. And sometimes we do talk to the nonprofits with the initial idea of, oh, here's the game theory potential solution of using game theory to your problem. But then they told us that this is not their main pain point. They want to do something else, but they also need our help. They also need AI's help. So we end up building other AI solutions for them, and it gets deployed. So we're still happy with that kind of outcome.
Nice. Yeah, that's great. I think the point about the hammer and the nails is spot on. Absolutely. Next question is a little bit more of a technical one from Kareem. How can we extend the iterative grouping algorithm in the case of non-perfect rational agents, or in the case where they know they are being observed? Any ideas?
Yeah, that's actually a very, very good question. So when they know that they are being observed, in the extreme case, they just shut down the collusion functionality per se, right? So then you cannot detect anything. And if it is just some like randomness in the observation, then I think it's still possible to be handled. It's like in the worst case, you just let them play the same game multiple times and to see what they do, and then derive from there. And so you can have the higher confidence that A and B are in the same collusion. So that's what I immediately can think of. And I think that's a very good question. Maybe there's more to do in that space.
Nice, cool. Yeah, I think it's quite an exciting area, actually. This idea of coalition destruction and coalition detection and detecting collusion comes up in a bunch of interesting places.
Yeah.
Next question is about some of the more recent work that you were describing. Someone asks, could you elaborate on how you simulated the patients in order to train mental health care professionals? Thank you.
Yes. Yeah, that's a very good question. So here we are focusing on the cognitive behavior therapy training. And because of that, we are following the standard cognitive diagrams, which consists of several layers of mindset per se. So we have the patient's core belief, and then the intermediate belief, and then the automatic thoughts, which are for people who are familiar with cognitive behavioral therapy, maybe they get a sense of it. And then based on these, we also kind of generate the emotions and behaviors. So, and also the corresponding coping strategies in the situations. Basically, we first of all construct a finite pool of core beliefs and emotions, and then we prompt large language models to generate possible intermediate beliefs, and then generate a diverse set of them, and then based on that to generate the other parts of this cognitive model. And then once we get this complete cognitive model, that's when we started to just generate the actual simulated patient with the cognitive model as the basis. So the simulated patient, whenever they respond to the trainee, they always need to refer to their actual cognitive model there. And then initially when we did this with the cognitive model, we were like, this is good. And the simulated patient is acting according to the cognitive model. But then when we had the pilot study with the therapist, they were like, this is way too naive. The patient that we're dealing with is way harder than what you have. They don't reveal what they actually think so easily. So we had to add this conversational style, like you see in the middle here. Like some of them are like very pleasing, like they don't tell you what they actually think. They just don't tell you in a way that they think can please you. And those patient styles make the simulations way more realistic and also harder. So the trainees can choose the style that they want to practice with. And then as they had the conversation with them, they can formulate the cognitive model based on the conversation. Now we have the original cognitive model that we start with, and now we have the trainee's answer. We can do the comparison, and then based on that to give feedback to the trainee.
Nice, thanks. I think we've just got time for 2 more questions, if that's okay with you.
Yeah.
Wonderful. Okay. So first of these 2 questions. In coalition identification, are you worried about powerful bad actors using these algorithms? In particular, this could enable companies to bust unions, someone says.
Yes. So we are indeed worried about like the situations where the big companies may do something that like either they form a coalition or they try to outcompete their competitors. Like I was using the example earlier when I was there in Santa Cruz that if Tesla one day decided to have all their autonomous vehicles and have some algorithm behind it so that they can prioritize the pathways for Tesla vehicles and block other vehicles from other brands. And from the regulator's perspective, they probably don't want this to happen. So they want to make sure that these autonomous vehicles are using AI algorithms that are not doing such collision. And what we're trying to do is kind of a first step, trying to see what the regulator can do. And of course, what we currently have is still far away from the more realistic scenario. And also, we are excited about how the discussions on how to bring our initial model closer to the actual scenario.
Great, thanks. And a nice question from James to round us off. What's your thought process or procedure for prioritizing new lines of research and/or applications?
Yeah, that's very good question. So for me, I think there are something that I'm definitely interested in and focus on, that is multi-agent systems and real world problems. So that's what I'm kind of insisting on. And initially, like my thought process is that every single project, it ideally has both the research, like fundamental new theorems, and real world applications. But that's not always something that we can do in the end. So we currently having the strategy where we continue working on the interesting technical problems and that are inspired or motivated by the real problem that we have worked on. And we, on the other hand, we are also actively reaching out to more nonprofit organizations to see if they are facing any problems that are somewhat having the multi-agent flavor, and then trying to see if we can design AI solutions for them. And what I see is that this, like, more theory and more application-oriented stuff go hand in hand, and new problems would emerge as I continue working on them. So that's how I'm doing it. I'm not trying to force one way or another. It's more like I want to work on multi-agent and real-world problems, so let's just go with that.
Okay, that's fantastic. All right, if everyone could give me one last round of applause for Fei, please.
Thank you all.